Hello everyone, and welcome to the next video in the problem solving skills series. And in this video I will be talking about 5 problems whose solutions require the use of addition, subtraction, multiplication, division, basically the 4 basic arithmetic operations. And we will talk about how we go about modeling these kinds of problems and how do we go about solving the models. So the title for this video series is a sampling of problems whose solutions require the use of addition, subtraction, multiplication, and division. Alright, let's start with problem number 1. Problem 1 says there are 5 boxes, each of which has a mass of 12.5 kilograms. There are 3 boxes, each of which has a mass of 15.8 kilograms. Calculate the average mass of a box. Now for this problem, we will begin with the quantity symbol, which because we want to find an average mass, the quantity symbol is m. However, we do put a line on top, as you can see here, indicating that this is not just mass but an average mass. So the line on top of a quantity symbol implies that we are working out an average value. Now of course this represents the average mass of a box, and the unit for it officially would be kilograms per 1. And per 1 because if you think about kilograms per box, which would be the more common way of writing it down, let me actually show you here, kilograms per box. However, keep in mind that boxes, when we talk about per box, we're talking about for 1 box, and therefore we are counting, and the official unit of counting is 1. Now I am going to replace this with box because later on when we have our closing statement, because that's the more common way of talking about it. Usually when we talk about 1, instead of writing 1, we write the nature of the 1, such as 1 orange or 1 box. We just write down orange or box. So of course we would normally say kilograms per box, and you should continue to do that. But just to bring about the awareness that this is the unit of counting, I'm using 1 here. Alright, so the average mass, like all average problems, you can think of an average problem as being the sum of data divided by the number of data. So eventually we're going to divide 2 values. On the top, in the dividend, we write down the sum of the data, and down here in the divisor, we write the number of data. Now that's easy to understand, but quite how we go about finding the sum of data and precisely what those data are and what do we divide by, these are good questions, and we're going to talk about them. However, one way to figure out what should go on top and what goes down here is to take a look at the unit for the average. An average value always has the per notation in it. It's always something like kilograms per box, dollars per hour, kilometers per hour, and so this division symbol is actually corresponds to this division over here, and it shows that on top of the division where the dividend is, we need to find the total of this quantity, total kilograms. In the context of the word problem that we have, the total kilograms refers to the total mass of all the boxes. So on top here we'll put down the total mass of all of the boxes, and then for the divisor, if you take a look at the unit here, it talks about box, and that represents, as we said, this is counting, so it represents the number of boxes. So the total of this quantity will go down here, and we put down the total number of boxes down here. So again, we find the total mass of all the boxes and divide that by the total number of boxes, and that gives us the average mass of a box. Once again, you can figure out what goes on top if you take a look at the unit here, and what goes down here if you take a look at the unit over here. And you always go by the total of what the top here says divided by the total of the quantity down here. So the total mass of all the boxes divided by the total number of boxes. So here again we write down the total mass of all the boxes as the dividend and the total number of boxes as the divisor. Alright, now If we can go back to the word problem itself, it says now the total mass of all the boxes then goes on top. And how do we find the total mass of all the boxes? We have 5 boxes, each of which has a mass of 12.5 kilograms. And so the total mass of these boxes, we can compute that by multiplying 12.5 by 5. And therefore we write down 12.5 times 5. This gives me the mass of the 5 boxes, each of which has a mass of 12.5 kilograms. Now to this, we're going to add the mass of the 3 boxes. Each of these ones has a mass of 15.8 kilograms, and the total mass of these boxes would come from 15.8 multiplied by 3. And therefore we write that down next, and here we have it. So now on the top, where the dividend is, we have the total mass of all the boxes. We divide this by the total number of boxes. There are 5 boxes from here, and to this we add the 3 boxes, and we end up with this expression. So this becomes the model for the problem. Let's take a quick look at how we came up with the model one more time. The average mass that we seek is equal to total mass of all the boxes divided by the total number of boxes. If you get confused as to how you can figure this out, the unit will give you a good idea. So we have, let me actually replace the one with box for a minute. Okay, so we have kilograms per box. And so the top here, the dividend, should be the total of what this says. And because we're talking about masses of boxes, the kilograms implies the total kilograms would be the total mass of all the boxes. And down here we have the number of boxes, and for our expressions we put the total of this quantity. Total number of boxes goes down here, so it's always the total of the top divided by the total of the bottom. Now this whole thing is seen as one term. The whole thing is one term, and it has a dividend which is at the top and the divisor which is down here. The dividend breaks into 2 terms. We work out the terms and then we add them up. The divisor, the terms have already been worked out. One of them is 5, the other one is 3, and so we add them up at the next step. So now we write m is equal to, so we work out 12.5 times 5, that gives me 62.5, plus 15.8 times 3, which is 47.4, and the divisor comes to 8. Okay, now we add the top, and we write 109.9 divided by 8. So the total mass of all the boxes comes to 109.9 kilograms, and the total number of boxes is 8. That's where the unit comes from. We are dividing the kilograms, the total mass in kilograms, by the total number of boxes using the unit of counting. Now we divide, and we have that the average mass of a box is rounded 13.7 kilograms per box. A closing statement follows. The average mass of a box is 13.7 kilograms per box. Alright, so that's the end of problem 1. Okay, let's now move to problem 2. And this one says, this morning you drove at a speed of 120 kilometers per hour for 2.5 hours. This afternoon you drove at a speed of 90 kilometers per hour for 1.5 hours. What was your average speed today? So once again we are talking about an average, and this time the quantity that we seek is speed. We are seeking the average speed, and the quantity symbol for speed is either lowercase s or lowercase v. And because we are seeking the average speed, we put a line on top of either s or v. V is more common, and I'm going to use v in my solution. So v with a line on top, this is read as average speed. That's my average speed today, represents the value of my average speed today, and the unit for speed of course is kilometers per hour. Alright, now again we have an average problem, and that means that we have to put the sum of the data on the top, divide by the number of data. So once again, to figure out what should go on top and what should go down here, we can use the unit. The total kilometers, that would be total distance that I covered, will go on top. And the total hours, which is total travel time, goes down here. To find the total kilometers, total distance that I covered, we find distance covered in the morning, and then we add to that the distance that we covered this afternoon. Now, as far as working out the distance goes, something that that is good to know, and actually you should know this if you don't know it already, is that if you have a speed of, let's say, if you're traveling at a speed of 100 kilometers per hour, and let's say that you travel for 2 hours, then the total distance that you cover, you can find it by multiplying your speed and travel time. Again, if you think about it, it does make sense, because 100 kilometers per hour basically says that you cover 100 kilometers in 1 hour. And if you travel for 2 hours, then the total distance becomes 100 times 2, or 200 kilometers. And therefore, if you want to find your distance, you can multiply your speed by travel time. And here we have so we multiply the speed by travel time, and that gives me 200 kilometers as the distance that I covered. Okay, let me go back to the problem now. So if you keep that in mind, that by multiplying your speed and travel time, you can find the distance that you covered, it makes sense that for the morning, for the distance that I covered this morning, I should multiply my speed this morning, which was 120 kilometers per hour, by travel time this morning, which was 2.5 hours. And that becomes term number 1 on the top. My speed this morning multiplied by travel time gives me the total distance that I covered this morning. Now, to this we're going to add distance that we covered this afternoon. And because this afternoon we drove at a speed of 90 kilometers per hour for 1.5 hours, we can find the distance that we covered this afternoon by multiplying the speed 90 and travel time 1.5. And we write 90 times 1.5. So now we have computed the total distance that we covered in kilometers. Now we need to divide by the total travel time. And we drove for 2.5 hours this morning and 1.5 hours this afternoon, and therefore the total travel time comes to 2.5 plus 1.5. Now I have the total kilometers, total distance covered today in kilometers on top, made up of 2 terms, distance covered this morning plus distance covered this afternoon, divide by total travel time. And if we divide total distance that we covered by total travel time, we find our average speed. The top has 2 terms, we work both of them at the same time, and the divisor, we can finish that by adding 2.5 and 1.5. So the next line reads as the average speed is equal to 300, coming from 120 times 2.5 plus 135, which comes from 90 times 1.5. 300 kilometers then is the distance that I covered this morning, and 135 kilometers is the distance that I covered this afternoon. The total travel time was 4 hours for the whole day. We add the distances that we covered in the morning and in the afternoon to get a total distance of 435 kilometers. Now, total distance that we covered this today, 435 kilometers, we divide that by total travel time to find our average speed, which comes to 109 kilometers per hour. And a closing statement follows. My average speed was 109 kilometers per hour today. Okay. Now, let me go back to the previous problem number 1 for a minute, so that I can tell you a little bit about some properties of average problems that are good to know. Suppose that for problem number 1, suppose that we solved the problem and we found out that the average mass of a box is, let's say, 17 kilograms per box. And we should know that this value cannot be correct. And if you think about it, the reason is because an average value is always between minimum and maximum values that you have in your list. If my minimum mass is 12.5 kilograms and the maximum mass is 15.8 kilograms, then there is no way that the average value will be 17, which is higher than the maximum 15.8. Also, an average value cannot be less than the minimum. So if you end up with an average value that's, let's say, 7 kilograms per box, then that cannot be correct, because the minimum that we have is 12.5 kilograms, and an average cannot be below the minimum. Also, you should keep in mind that the average value is not always in between. It really depends on how many boxes have a mass of 12.5 kilograms and how many have a mass of 15.8 kilograms. Suppose, as an example, that you have 100 boxes. So I'm going to show you, tell you about two scenarios. Scenario number one, you have 100 boxes. One of them has a mass of 12.5. The other 99 have a mass of 15.8. And so you should expect that because there are so many that have the bigger mass, the average will be much closer to 15.8. Now scenario number two, just the opposite. Suppose that of the 100 boxes that you have, 99 of them are the light kind, 12.5 kilograms, and only one has the heavy mass of 15.8 kilograms. Then you should expect that your average will be closer to 12.5, of course. So an average value is not always in the middle. In fact, if the number of boxes are the same, then you can say that the average value is right at the center, at the middle point between 12.5 and 15.8. Same thing is true about problem number two. If I'm looking for my average speed, then if I find that for this particular problem, my average speed is, let's say, 130 kilometers per hour, then I should know that something went wrong in the solution, because the maximum speed that I drove at was 120 kilometers per hour, and there is no way that the average will be more than that. Same thing for the lowest speed of 90 kilometers per hour. There is no way that the average that you find will be less than 90 kilometers per hour. And again, if for most of the time I drove at 120 and for only a short duration I went at 90, you should expect the average to be much closer to 120. If, on the other hand, for most of the time I drove at 90 and just for a short time I drove at 120, then of course one would expect that the average is closer to 90. In case the travel time this morning at 120 and the travel time this afternoon when I drove at 90 kilometers per hour, in case the two travel times are the same, then the average speed will come to exactly the middle point between 90 and 120 kilometers. Alright, let's move on to problem number 3 now. Okay, so problem number 3 says this is about GPA. And this problem says that, oops, my apologies, let me get it back. Problem number 3 says last term Steve took Math 101, Chem 101, and Bio 101. Math 101 is worth 4 credits, Chem 101 is worth 3 credits, and Bio 101 is worth 2 credits. Steve got an A in Math 101 worth 4.00 grade points, a B minus in Chem 101 worth 2.67 grade points, and a C in Bio 101 worth 2.00 grade points. And we want to find Steve's term GPA last term. Okay, I have to tell you a lot about what these values mean and what these grade points are. So let's start with a chart. And in this chart we have I have sort of come up with equivalencies between percent grades, letter grades, and also what we call grade points. Percent grades, let's take a look at let's say this row. This row says that in case the grade that you get in a course is between 70 and 72, 70% and 72%, and that includes the endpoints 70 and 72, then your letter grade will be a B minus. And in case your grade happens to be between 73% and 76%, with 73 and 76 both included, then your grade will be a B, and so on for the rest of the percentages. 49% and below correspond to all of those grades correspond to an F. Now grade points are similar to percent grades, except that instead of going from 0% to 100%, which is a fine kind of a scale, they go from 0 to 4. And this one is also in some ways a fine scale too, because it does include 2 decimal digits. But it goes from 0 to 4.33. Now the 4.33, very few institutions these days use 4.33. It has become customary for everyone to lower that to 4.00, which in fact means that someone getting a grade of 86% will get the same grade point as someone who gets 100%, which is not quite fair, but that's the way things have gone, and most of the institutions that go with grade point average GPA, they assign 4.00 both to an A and also an A plus. On the low end as well, some institutions have done away with D minus. Obviously, F plus doesn't really make much of sense, and so D minus has been assigned a grade point value of 1. I guess one reason for that would be because computations might become a bit easier, because then we go from 1 to 4 instead of 0.67 to 4.33. However, while it's not quite fair at the top end to give 4.00 the same grade point 4.00 to both the range of 86 to 89% and 90 and above, on the low end it doesn't really make a difference. In the D range, whether you got a 1 or 0.67, it doesn't matter that much, I guess. Alright, now the grade points, I will give you an indication of how people have come up with these values, but you might have noticed that the ones without the plus or a minus, like F, D, C, B, and A, are given the values 0 for F, 1 for D, 2 for C, 3 for B, and 4 for A. So that's the initial setup, and then they fill the in-betweens like B minus and C plus, and I will show you how later on. Now, when we talk about GPA or grade point average, we're talking about finding an average of these grades, the grade points. So GPA is short for grade point average, and that's an average of these grade points. So if you take 2 courses, and in one of them, let's say you get an A, which is worth 4.00 grade points, and in the other one, let's say you get a C, which is worth 2.00 grade points, then we would average out in some way. We find an average of the values 4.00 and 2.00, and that becomes your grade point average. Now the question of in exactly what way do we do the computation? Do we add the 2 grades and divide by 2, or is there some other way of doing it? To explain how we go about how it is not always fair to just add the grade points and divide by the number of them, like in this case, it may or may not be fair for us to add 4 and 2, the 4.00 and 2.00, which were the 2 grades that you got in your 2 courses. It may or may not be fair for us to add them and divide by 2. Let's see why sometimes that may not be fair. Okay, let's take a look at a hypothetical situation where 2 students, student 1 and student 2, both of them take Bio 101 and Chem 101. Now, just for the sake of argument, I'm sort of exaggerating a bit. Let's say that Bio 101 classes run for 1 hour per week, and Chem 101 39 hours per week. That's a lot of hours, but I just wanted 2 values that are very far apart. Okay, so student 1 in Bio 101 gets an A, or maybe even A plus with 4.00, but in Chem they don't do so well. They get a C, which is worth only 2.00. Student 2 just does the opposite. In Bio 101, this student doesn't do well. They get 2.00. But in Chem 101, they do really well, an A or an A plus, worth 4.00. And the question is, will they both end up with the same GPA? If we add 4 and 2 and divide by 2, we get 6 divided by 2, which is 3.00. And here, if we add 2 and 4 for student 2, we add 2 and 4, we get 6 divided by 2. This student also gets 3.00. Now the question is that fair to give both students a grade point average, a GPA of 3.00? And if you think about it, due to the fact that the hours are not the same, this will not be a fair situation. Think about it. Who studied harder, student 1 or student 2? Student 1, in order to get an A in bio, had to do very little work. I mean, if you think about it, how much can you teach and how much can you learn in 1 hour per week? So the student didn't have to do a lot of work to understand the material that was taught during the 1 hour per week bio class. But for the chem course, there was a lot of information coming the students' way. 39 hours per week of information was being taught and learned in class. And the student obviously did not keep up with all of that work, and they got a C. Let's take a look at student number 2. In bio, which would have been very easy to get a good mark in because there is only so much that you can teach in 1 hour, this student did not do a good job and they got a C, which is worth only 2.00. But in the chem course, which was running for 39 hours per week, they had to do a ton of work to get an A or an A+. They had to, this student number 2, had to keep up with all of that information that came their way during the 39 hours of classes per week. And they shone in that course. They got 4.00. And so the student number 2 worked a lot harder to get a 4.00 in chem compared to student 1 who got a 4.00 in bio, which means that student number 2 should get a higher GPA. Now, to make things fair, what we do is we're going to count the grade that student 1 got in bio 101 only once, and we count the grade that student 1 got in chem 101 39 times. Same with student number 2. The grade that this student got in bio 101 we'll count once. The grade that student 2 got in chem 101 we'll count 39 times. And that way we sort of give the same weight to every hour of instruction, in whether it happens in bio or chem. So basically we are giving, let's say, 2.00 for 39 for each of the hours of operation. In each of the hours the student got a 2.00, and this student, for each hour of instruction here, they understood pretty much every hour of instruction and they got 4.00. So to calculate the GPA then, what we do is for student number 1 we get the grade 4.00 we'll count once, that's 4.00 times 1, and then to this we add the 2.00 but 39 times, that's 2 times 39, and the total counts is once for 4.00 and 39 2.00s for a total of 1 plus 39. For student number 2 it's the opposite. The 2.00 will count once, that's 2 times 1 here, and the 4.00 will count 39 times, so we have 4 times 39, and then we divide by the total counts once for the 2.00, and there are 39 pieces of data, each one is 4.00 for a total of 1 plus 39, which is 40 as well. Now you can see that the dividend for student number 1 turns out to be only 82, but for student number 2 it's 158, and the result of the GPA, the result is for student number 1 the GPA is 2.05, and for student number 2 the GPA is 3.95. Now this is quite a fair way to find an average for each of the students, considering how much work they had to put in. Alright. Now the hours per week, assuming of course that your courses are set up so that in 1 hour of teaching in one course it has as much value as 1 hour of teaching in the other course, then we refer to the 1 and the 39 as credit values. And as you can see, your grade points are multiplied by the credit value in that course. 4 is multiplied by 1, 2 is multiplied by the credit value of 39 for Chem 101. And that's why for this situation, for this scenario, they would say that Bio 101 is worth 1 credit, but Chem 101 is worth 39 credits. Alright, now with that introduction to grades in mind, let's go back to the problem that we have here. And so problem number 3 says that last term Steve took Math 101, Chem 101 and Bio 101. The credit values are 4, 3 and 2. So Math 101 runs for 4 hours per week, Chem 101 for 3 hours per week, and Bio 101 2 hours per week. And I should also mention that these credit values are for courses that are 1 semester long. If a course is year long or 2 semesters long, then each of these crate values should be multiplied by 2. Now Steve got an A in Math 101 worth 4.00 grade points. Now this 4.00 for Math 101 will count 4 times. That's the crate value for Math 101. And for Chem 101, Steve got 2.67, and this one will count 3 times. For Bio 101, he got a C, and that's worth 2.00 grade points. The 2.00 will count twice. Now we'll go for our solution. So now we have the average grade, or GPA in this case, is equal to, that's my GPA last term with a unit 1. I will not be discussing the unit 1 now, just to keep the video short. My concern is mostly in these videos to talk about the units that go with science problems. And so I will save the time to talk about those later on. Maybe at some point I'll come back and talk about it in some other video. Now we write down that the first term on the top is the 4.00 grade in Math 101, which we are going to count 4 times. And then to this we add the total grade points from Chem 101. The grade was 2.67, and we multiply that, we count that 3 times. So the next thing that we have is 2.67 times 3, and to this we add the last, which is the grade point value of 2.00 in Bio 101, which is going to be counted twice. And there you have it. Now we divide this by the total number of counts. The 4 was counted 4 times, 2.67 was counted 3 times, and the 2.00 was counted twice. So the total number of counts is 4 plus 3 plus 2. On the top we have 3 terms. We work them out to 16, and then 2.67 times 3, which is 8.01, and the last term, 2 times 2, is 4. And we divide that by 4 plus 3 plus 2, which is 9. The total grade points come to 28.01, divided by 9, and the GPA becomes 3.11. And so I had a GPA of 3.11 last term. And that's how you work out your GPA. Alright, that's the end of problem number 3. Except I would like to also, as I said, I would like to mention how we come up with the values for the B plus and C minus and such letter grades. So let's take a quick look at how they came up with those values. And for this, we're going to take a look at the scale from C to B. As I said before, C is worth 2.00 grade points, and a B is worth 3.00 grade points. Now C plus would be a third of the way up from C, or you can say 2/3 down from B. And a B minus is 1/3 down from B, or 2/3 up from C. So we have the following image. Here's C plus, and there's B minus. And because we go from 2 to 3 at distance of 1, from C to C plus, it's 1/3, and therefore the value for C plus becomes 2 plus 1/3. And that works out to, as a decimal, 2.33. As I said, we round grade points to 2 decimal digits. And also here, we have 3.00, and we can find the grade point value for B minus if we subtract 1/3 from 3.00, and therefore we get 3 minus 1/3. Or you can also say 2 plus 2/3. In any case, once you convert to a decimal and round, you get a value of 2.67. And there we have it. So 2.33 comes from 2 plus 1/3 converted to a decimal and rounded. You can also say that 2.33 comes from 3 minus 2/3 converted to a decimal and rounded. For B minus, 2.67 comes from either 3 minus 1/3, which is then converted to a decimal and rounded, or 2 plus 2/3, and again that's converted to a decimal and rounded. This is how you find the mid values. Now, going back to the whole table, normally the B range and the C range and so on, these ones follow the rules that I told you about. However, as I said, at the top end, and also the low end, usually changes are made, so that the grade point values, the grade points for A and A plus are usually set to 4.00 for both, and D minus is given the same value as 1.00. Now, having said this, one thing that you should always keep in mind is that if you're attending a particular institution, you should always ask them for a table like this, and also the rules that they use when they do the computations. One example of what I'm talking about is in some institutions, when there is when they find let's say your grade point value for the top end, there may still be some that use 4.33 as the maximum, and therefore you need to know that. Alright, let's now move on to the next problem. Problem number 4, and there will be one more after this. Problem 4 says test 1 is worth 5% of the final grade and test 2 is worth 10% of the final grade. Alberto got 70% on test 1 and 90% on test 2. What is Alberto's average so far? Now, this is about tests that you write in a given course. GPA is about your average across multiple courses, and this is about your average in a single course. Let's say that there are a number of tests in that course, and we are only looking at the first 2 of them. Test 1 is worth 5% of the final grade, and test 2 is worth 10% of the final grade. Now, one way to make sense of this, and there are different ways of looking at it, by the way, I'm going to tell you about only one way of doing this right now, and later on when we talk about percentage, I will tell you about other ways of doing it, which are more efficient, by the way, at least in some problems. Now, one way to think about the 5% when you see your course outline, for example, saying that test 1 is worth 5% of the final grade, one way to think about it is that your grade on test number 1 will count 5 times when we compute your average. And if it says that test 2 is worth 10% of the final grade, you can think of this as meaning that your grade on test 2 will count 10 times when we find your average. And therefore, if Alberto got 70% on test 1 and 90% on test 2, the 70% will count 5 times and the 90% will count 10 times. And so we should expect that the average, Alberto's average, will not be 80%, which is halfway in between. Because of the fact that 90 is counted more times, the average will be closer to 90. So it will be over 80. It will be closer to 90 compared to 70. Okay, so the solution to this problem, we pick average grade as well. I should have said maybe Alberto's average. Let's change that. Alright, so that's Alberto's average, and the unit again 1, and G becomes equal to, now we're going to count 70% 5 times. So next we write down 70% times 5, and then to this we are going to count the 90% 10 times. So next we have 90% times 10. Divide by the total number of counts. So there are 5 of these, 5 70% and 10 90%, and the total count is 5 plus 10. Okay, so G becomes equal to, the average grade becomes equal to 70% times 5 is 350%, and 90% times 10 is 900%. Divide by 15, and we add the top to get 1250%, divided by 15, and the average grade is 83%. You notice that it's not 80%, which is halfway between 70 and 90, and it is in fact higher than 80, closer to 90 compared to 70, because of the fact that the 90% is counted more times, and that will pull the average towards itself. One quick note before I give you the closing statement is you notice that the data, the actual data that are being averaged, I kept the percentage in them because I wanted my final answer to come out in percentage. But the number of counts, I did drop the percentage. Now the other ways of doing it would be to keep the percentage for 5, 10 here and also down here. It would just make it a little bit more complicated because when you multiply it, then you get 350%, and this one becomes 900%. divide by 15%, and one of the percents will cancel out. Another approach would be to change the percentages to decimals and then use 0.05 here and 0.1 divide by 0.05 plus 0.1. I will be talking about these other approaches later on in some of the videos, again when we take up percentage, but for now this interpretation works just as well. Closing statement: Alberto has an average of 83% so far. And now we come to the last problem in this video. Problem 5 says a sample of carbon atoms from nature contains 98.93% C12 and 1.07% C13. Calculate the atomic mass of carbon. Alright, let's talk about C12 and C13. Now carbon, of course, is carbon because it has 6 protons. We refer to 6 as the atomic number for carbon. It's, as I said before, this is a very descriptive kind of label because it tells us that it's a number that tells you what kind of atom you have. So a carbon atom is a carbon atom because it has 6 carbons. And we usually write, when we write things by hand, we usually write the atomic number down here as a subscript on the left side of the atomic symbol. So all of these carbons have 6 protons. If you change the 6 to, let's say, 7, you no longer have carbon, now you have nitrogen. And 8 would give you oxygen and so on. Now, although the number of protons in a given atom has to be fixed, the number of neutrons can vary. So we can have a carbon atom that has 6 protons and 6 neutrons for a total of 12 protons and neutrons. This carbon atom has 6 protons and 7 neutrons for a total of 13 protons and neutrons. And this carbon atom has got 6 protons and 8 neutrons for a total of 14 protons and neutrons. And so the number that you see up here, which is the total number of protons and neutrons, we refer to this as the mass number. Now, the word mass number may be a bit confusing because it gives the impression that we're talking about mass. I will talk about this in a bit, but for now, please keep in mind that this is not mass. The number that you see here is the total number of protons and neutrons. We are counting. We are saying that we have 12 protons and neutrons. We're not talking about the mass of them, not at this stage at all. So we call it mass number for now, but keep in mind that it's not mass really. It's the total number of protons and neutrons. We refer to this number then as the atomic number and the top number as the mass number. Now the atomic number is usually not written down because it's fixed. It's expected that everyone knows that carbon has an atomic number of 6. And if someone forgets, you can always go to the periodic table or search it on the net and find that a carbon atom has 6 protons. But the number of neutrons, because it can be different depending on what carbon atom you're looking at, we would normally, if there is a need to specify that this particular carbon atom that I'm talking about has 13 protons and neutrons, then we write the number at the top. So normally we write this: C12, C13, and C14. Alright, 2 other notations that are common are for C12, we put down C-12, for C13, C-13, and for C14, C-14. It's also common to write down carbon, so we spread it out if you like, carbon and then followed by hyphen and then 12. Same thing for carbon-13 and then carbon-14. Now, the official notation is the top one. But because, especially before the advent of computers, it was difficult to write a superscript on the left side of a letter, these other 2 ways of writing things down were preferred. And you notice that all of these characters that you see in the second and the third notations, such as the letter C, the hyphen, and then 1 and 2, these are all characters that are available on the keyboard. And so for newsprint, for example, they usually prefer to, or in the olden days anyway, they prefer to use C12, and for the general public who may not know what C stands for, they actually write down carbon 12. I will continue to use the top notation, but all three notations are quite frequently used. All right. Now, one carbon atom, let me go to the previous image for a minute. So any carbon atom could be either C12 or it could be C13 or it could be C14. Now, there are other ones, but in nature, usually, the ones that we usually care about are the ones that you see in nature. And in nature, you find C12, quite a lot of it, and C13 very little amounts, and C14 is present in trace amounts, and normally we wouldn't even care about it much, except that C14 happens to be a very important kind of carbon atom, and therefore this is actually the one that they use to date the age of old objects like dinosaur bones. Some of these radiate and some of them don't. C14 radiates, and this property allows us to measure the age of old objects. Now we refer to these to different atoms of the same kind with a different number of neutrons as isotopes. So right now you're looking at three different isotopes of carbon. C12 is one isotope, C13 is a different isotope, and C14 is yet another isotope. Now, masses of these, if you think about C12, it has 12 protons and neutrons. One proton has a mass of 1 AMU. One neutron has a mass of roughly 1 AMU. So if a proton has a mass of 1 AMU and a neutron has a mass of 1 AMU, 12 of them will have a mass of 12 AMU. This is why this number, which tells you how many, is called a mass number, because although it tells you how many, it can quickly tell you what the mass is. If you have 12 protons and neutrons, that's how many. The mass is 12 AMU. That's how heavy. If you have 13 protons and neutrons, again, this is how many. Then the mass is 13 AMU. That's how heavy. So again, this is a number. The unit is counting. It tells us how many particles we have of the proton and neutron kind. But if I know that I have 12 particles, that's 12 AMU. So I can tell the mass from the number, which is why this is called the mass number. And so a C12 atom has 12 protons and neutrons. Its mass will be 12 AMU. C13 has a mass number of 13. 13 protons and neutrons. The mass will be 13 AMU. And C14 has a mass number of 14. That means that we have 14 protons and neutrons. Its mass will be 14 AMU. Okay. Now, let's say that we want to work with the mass of a carbon atom. Let's say that we have CO2, carbon dioxide, and there is one carbon in a molecule of CO2, and we would like to find the mass of a CO2 molecule. Right away, the question comes as to what we call the mass of a carbon atom. 12 AMU or 13 AMU? Should we go with the one that's most abundant? And in the case of C12 and C13, that may be reasonable in some ways, because we could argue that C12 is present some 99% of the time and C13 only 1% of the time. And therefore, we won't be too far off if we go with 12. But in some cases, that's not true. The numbers are not so different as 99 and 1. Although in many cases, that is the case, that one isotope dominates. But in the case of chlorine, for example, they are present in about, roughly, if I remember right, about 2/3 of the time it's Cl35 and 1/3 of the time Cl37, I think. And in those cases, it won't be reasonable for us to go with the mass with the mass of the one that's most abundant. However, if we find some average mass, then that would be a reasonable kind of a mass to work with. And it's been the case that an average mass for the carbon atom is a reasonable one to work with in most applications. All right, let's go back to the to the word problem now. So now we have a sample of carbon atoms from nature contains 98.93% C12 and 1.07% C13. So almost roughly 99% C12, 1% C13. And you can think of this as being that, as saying that if you were going to look at 100 atoms of carbon from a sample from nature, then 99 of them, 99 out of 100 would be C12 and only 1 would be C13. We want to find the atomic mass of carbon. The phrase atomic mass is important. Atomic mass is a quantity, and the quantity atomic mass is the average mass of a certain atom from a sample from nature. This is important, not a sample from lab, which may have a different composition of the isotopes, different percentages for, let's say, C12 and C13. But if your sample comes from nature, then we refer to the average mass that you find of all of the isotopes in the sample that you got as the atomic mass. The notation that we use for atomic mass is MA. This is by convention, so you don't have to put the line on top now. This is the atomic mass. So here MA is the atomic mass of carbon, and the unit for it, of course, is AMU per 1, or if you want, we can change that to atoms. So it's AMU per atom. Again, we normally state the nature of the one. So MA is the atomic mass of carbon. And again, from what sample? If I use the phrase atomic mass, the sample is from nature. If the sample doesn't come from nature, then you should not use the phrase atomic mass, but you just say average mass of a carbon atom from the sample that I have. So atomic mass of carbon implied that the sample comes from nature. The unit is AMU per atom. And again, the top unit, AMU, tells you what should go on as your dividend on top of your division, the total mass of the carbon atoms from the sample that you have, and the total number of atoms in that sample. Because you place that as the divisor. Okay, so we have now the mass of all of. Now let's say that we take a sample that's only 100 atoms. Of these, 99, almost 99. We are going to use 98.93, but it's roughly 99 of them will be C12. So the total mass of C12 atoms from a sample that has 100 atoms will be 12 times roughly 99. Or if you want to be more accurate, 98.93 times 12. That becomes term number 1. So 12 times 98.93, and to this we add the mass from C13 in a sample of 100 atoms, and that would be about one of them is 13, has a mass of 13 AMU, and therefore we have 13 times 1, but the accurate value of course is 1.07, so we have 13 times 1.07. And the total number of atoms comes from adding the percentages, and we get 98.93 plus 1.07, and that's actually 100, but we would like to explain where it comes from, so I don't write 100, but 98.93 and 1.07. This may be a good point actually to mention that when you make your model, at the end you should spend maybe a few seconds to double check to make sure that you haven't done any calculations in your head. In other words, you shouldn't really add these two and put down 100. Anytime you do such a thing, what happens is that it turns into a step-by-step approach. It's no longer algebraic. And one problem with writing down 100 here is later on in this series when we talk about more complicated problems, like when the average mass is known, but we don't know the percentage, 1.07, then this becomes your unknown. And if you have 100 here, it doesn't show that the unknown also appears as in the divisor. But if you write 98.93 plus 1.07, later, if 1.07 becomes the unknown, you know that both of these instances will change into a quantity symbol. So that's one thing that you should do. To make sure that no work has been done in your head on the site, you should always take a look at every number that you use in your model and make sure you can find those values in the body of the word problem. The 12 comes from here. 98.93 comes from here. You can find 13 and 1.07 here and here. Now if I wrote 100 down here, then I would not be able to find 100 anywhere in this word problem, and therefore that will pose a problem later on. So that's one thing to do. The other thing to do, by the way, just to make sure that your model has all the basic needs have been met, you should make sure that any number that you plan to use in solving this problem will appear on the first line in your model. No number will be introduced later on. All right, so the top now, the total mass of C12 atoms comes to, from a sample of 100 atoms, comes to 1187.16 AMU, and the total mass of carbon-13 atoms from the sample of 100 atoms comes to 13.91 AMU. We add them up to find the total mass of all of the carbon atoms as 1201.07. Divide by not 4, that should be 100. Let me fix that problem right now. All right, okay. And then we move on to the next line, which says that the average mass of a carbon atom is 12.01. Now I have rounded this. They're all rules of rounding, because these ones, depending on the number of significant digits and how you add your numbers, you keep a certain number of digits. I won't be talking about that in this video, but this is the rounded value, and the average mass of a carbon atom from a sample from nature is in fact 12.01 AMU. The quoted value is usually 12.01 AMU per atom. Closing statement, the atomic mass of carbon is 12.01 AMU per atom. Now the 12.01 AMU per atom, which is what we will call the mass of a carbon atom, you notice that this is an average mass. In the periodic table, this is where you find it, under the chemical symbol for the atom. So this is 12.01. You can think of it as either AMU per atom or grams per mole. It's pretty interesting, actually, when you think about it, that the 12.01, which is the average mass of a carbon atom, and that's the reported value in the periodic table, is in fact not the mass of any particular carbon atom. A particular carbon atom will be either C12 or C13 or C14, and if it's, let's say, C12, then its mass is 12 AMU. It's not 12.01. C13 has a mass of 13 AMU, and C14 has a mass of 14 AMU. So the average mass is not really the mass of any carbon atom from any sample from nature. But as I said, this average mass in calculations, it works pretty well, and the results that we get from it seem to be reasonable. So we continue to use it. One final note, in the periodic table, the atomic number is written on top of the chemical symbol for the atom. It's not written as a subscript on the left side, but on top. All right, and that brings us to the end of this video, I believe. And thank you very much again for watching. And in the next video coming up, what we'll do now is, now that we've gone through a sampling of word problems, and we've taken a look at quite a few different kinds of models and equations with brackets in them, with nested brackets, which are brackets within brackets. We now have talked about the notation for the models for problems that require that we divide, like the 5 that we talked about in this video. Now, with this kind of background, you should already feel a bit more comfortable working with algebraic equations, and not just working with them, but also making them. Now, what we'll do is we're going to go back to the beginning, and we're going to start a very systematic study of these kinds of problems. We're going to go to addition, take a much deeper look at problems that require that we add, subtract, multiply, divide, and then we move on to problems that have more complex operations like exponents, roots, logarithms, and so on. And following the theme of the videos, that our needs keep growing as we go from the simplest of kinds of problems that we solve to more and more complicated kinds of problems that we solve. Thank you again for watching, and if you have any comments, please write them down. And I wish you all a great day, and I will be gone in 3, 2, 1.